iPod 3 maybe?
Something like that.
We had a Nano for a long time. We might have had one before that too. I don't remember. First phone, first smartphone was an iPhone. EG.
My first phone was a flip phone. I don't remember what.
Well, yeah, my first phone was a flip phone.
My first smartphone was the LG, because it was like dirt cheap, like maybe $30-40.
First flip phone was a Motorola Razr, I think.
Any questions?
Do you have an extra set pulled up?
I don't have it pulled up, so I'll have a few hours and maybe I'll remember.
I don't have it either, I was hoping.
I have it.
Oh,
It was the one, like it was a derivative problem, I think 5 maybe? That I didn't do.
Given 2 charges in the x-axis, that one? No, I don't think that's a derivative one.
It's like the shortest problem.
Derive the equation for electric
Yeah.
field at a distance r away, yeah, number 4.
using Gauss's law. We actually did that in class. The infinity forms
yeah.
required.
We did?
Yep.
Probably more than us.
And we did it the long way in chapter 23 or 24.
Okay.
Probably with 23, we found a force on a charge. Just divide by
That was our video, right, so I can just look back on it.
Yeah, as well as there's probably a video where, you know, one of the handed paper videos that I do.
Okay, alright, I'll look at it.
Nick,
Yeah, I think number 2, it says 14, is that milli?
Milli.
Millicoulombs?
10 to the negative third.
Negative. And for part B, for number 2, is that in the hollow part of the cube?
Yes. You're still within the cube.
Still in that cube?
Yeah.
So there's an electric flux in that? Because it's in the cube?
Yes, because the charge is in the cube, there is an electric flux.
Okay.
Is that sufficient?
Yeah.
Okay. Other questions? Try to get the name site right. There were no more questions. Right. I got a line of charge with uniform charge distribution. We didn't do one of these already. With find the electric potential, voltage distribution.
Maybe.
Well, let's go through
We
one.
talked about electric potential, I don't know whether we did a specific problem.
All right. Charge, and let's, just for the sake of the math fun there, uniform linear charge distribution. Let's make this a distance, 3 centimeters, 2 centimeters, 6 centimeters. I want to know the electric potential, we'll call that point P. What is the electric potential at point P? Assume, well, actually, what's the easiest answer?
assume you forgot.
0.
Don't forget units.
Is there really?
Throw the units in there.
I don't,
There we go, thank you. 0 volts. Why is that correct?
Because
it's outside the,
no, it's because it's the difference between, right? And it's like in respect to something else.
That voltage is in respect to something else. The electric potential is with respect to, say it again? Well, you could connect it, but you're going way complicated if you go in there. What's the formula for electric potential? I do know we did that.
KQ over R plus C, technically.
What does that plus C allow us to do?
To set our constant to anything.
Yep. If you just plugged in KQ over R into that equation, into that, or worked it out, come up with a number, yeah, that's fine, but I can always make the constant anything I want, so I can make it the constant so that the potential is 0 at that point. So if I gave you this problem and just set it like that, and you can say 0 volts, because you say so. However, let's prevent that, because that's not the intent here. Assuming VP equals 0 volts at R equals infinity. All right, that's establishing our constant to be 0 and making this actually more than a trivial problem.
Can we treat it as a trivial problem if they don't say that?
Yes. If it is my intent, and I just wanted to see if you catch that, great, spot on. If I don't state it, but that was not my intent, then on a test, you'll get credit for it because you answered the question correctly. However, on test corrections, I might say you're not allowed to do that.
Will the book usually do that with problems?
The book usually makes the assumption that it's 0 and R is equal to infinity.
Like always, or it'll actually say it in a problem?
I don't think it actually says it. That's traditional convention, but it's not written in stone. We have distribution of charge, so what level of math are we using? Good. I think if I heard you correctly.
Calculus integrals.
Yes. So the first thing we need to do is pick some little segment right here. dq, oh, I've given everything except the actual charge. So let's make the q total for the line of charge to be 7 microcoulombs. I know there's a potential there. So distance, there's a potential there, but there's an electric potential here because of this charge. That's a distance R. All right, the first step, I know that my potential, plugging into the formula, is going to be Coulomb's constant times dq over R. Makes sense. I want to get this in terms of a single variable. R is a variable, Q is a variable, K is constant, so I don't have to worry about that. But I need to somehow get Q in terms of R. Going with this distance here is, I'll just say dy. I was brainwashed like everyone else. So I need to somehow relate dq to dy, and we got the big clue here that it's a uniform linear charge distribution. So I know that that means that DQ over the total length is gonna be equal to that ratio, no matter where we're going. That's gonna get old fast.
So is it, sound wave traveling through the ground? Is that what?
That's my guess, but I hear beeping, so something's moving. Yeah. So, in the context of what I have here, this would be dq over dy. And so therefore dq is equal to lambda dy. Plug in what we know. We've got dv is equal to k lambda dy over r. So we've just changed the two variables, but at least, or we changed a variable, we still have two variables, we haven't reduced it yet, but at least the two variables now are both lengths. If I sort of set that as my reference right there, so this distance here is y. Even if I set this up and made this 0, I can always shift my axis. So I'm gonna make this my y. So now I can come up with a relationship between r and y, and which I'm just gonna label as x right now, it's gonna be 3 centimeters.
Why is there dy and y?
dy is just the length of that tiny little segment right there.
Oh.
Y itself is the distance from the point closest to point B.
Okay.
And what is the relationship between x, y, and r?
That right there.
So r becomes the square root of x squared plus y squared. Now mathematically, r would be plus or minus, but we know physically that r is a positive number. So dv equals k lambda dy over the square root of x squared plus y squared. We now have it in terms of a single variable, because lambda is constant, k is constant, x is constant, we only have y. So v is equal to k lambda integral of dy over square root of x squared plus y squared. And our limits of integration, I chose y to be this point right here, and so I'm going to be going from -2 to 6. Negative 0.02 to 0.06. This dramatic pause is for tying my shoe and to give you an opportunity to ask questions. All right, so how do I do that interval?
Look it up.
Sounds good.
I think it's just y. No, that's over 3 over 2.
Do the natural log, that's all right. There we go.
Intervals, I think.
So it's gonna be k lambda times the natural log of y plus make sure that I pick the right one there. So it's 1 over the square root. Yeah. These are absolute value signs right here. Oop, that should be positive. Now, plenty. So K, 8.99 times 10 to the ninth. Lambda is going to be the total charge divided by the total length. So my total charge I gave was 7 microcoulombs, so 7 times 10 to the negative 6. Divided by the length, which is 0.08 meters, times the natural log of 0.06 plus the square root of 0.03 plus squared plus 0.06 squared over, not over anything, minus the natural log of 0.02, negative 0.02 plus the square root of 0.03 squared plus 0.02 squared. Something back for a moment to make sure that obvious error. And now it's a calculator exercise. Someone's going to reveal the magic answer. What'd you get? 15.7. 15716. 15716. Oh, you're telling me.
Oh, no, I was just.
Yeah, I just rounded.
Okay, but I just, the way you wrote it,
Okay. Oh,
so I'm
well, well, I think Paul's gonna, you're working on it?
I got 1.63 million.
1.63 million?
Yeah, so it'd be 1.63 times 10 to the 6.
Do we have a third? Do we have 6 different values? The absolute value signs don't actually do anything here, but.
So just to be clear, we're finding the electric potential based on this section of the infinite line from -2 centimeters to 6 centimeters. And then lambda is the total charge over that distance.
Yes, the linear charge density.
That's fine, yeah, the distribution.
Alright, it's okay. Feeling confident in what he got.
And if we didn't look at that section, we looked at the whole line, then that's when you're saying it would be 0, because we could just use the constant thing.
If this were not here,
Or if we were not looking at that little like that segment from -2 to 6 centimeters, if we were just like taking the line as a infinite line being there,
right,
and what would the charge, the electric potential be there?
given that assumption, we just change the limits of integration from negative infinity to infinity, which,
Can you still do that? I work it out and get a number, or?
Should be able to, because this is the natural log of point of, it's natural log of y. So if that's infinity and that's infinity, we basically have two infinity divided by, that's infinity 0. Yeah, we got infinite potential.
What I did was I separated and multiplied it from.
So you got that except times 10 to the 18th.
Yeah, cause what I did, I multiplied those two first, and then I did that, and then I multiplied whatever I got from that, and whatever I got from that.
10 to the 18th is rather extreme. But you had the 1.63.
You're not plugging.
And the moral of this is show your work. We're not actually, given that you did it again, at least got that part the same, let's go with this. And let's finish it off, don't lose points over something trivial. Yeah. Back to the question of if we did the infinite line, then the only thing that changes is the only thing that will change are the limits of integration. This is so we're basically taking that to some huge number. And this also to some huge number. Now this is so that will be roughly equal to that in absolute value, but the negative, so you get negative huge number plus huge number is close to 0. So this is gonna shoot off to 0, this is gonna shoot off to infinity, so you end up with the natural log of something infinitely huge. So the electric potential for the full line would.
Conceptually, why is that? I mean, cause it's trailing off in either direction, getting farther away from the point that you're looking at. So
It is, they all have it, because there's no cancellation.